Underwater wireless power transfer for maritime applications. Abstract for unmanned underwater vehicles, UUVs, power is the critical factor that often determines mission lifetime. Unlike many terrestrial vehicles, where batteries can be easily replaced or recharged, UUVs must either surface for battery replacement, or make watertight connections to safely recharge. This project presents the development and implementation of an inductive, underwater wireless power transfer system for use with unmanned underwater vehicles, UUVs. Specially, the design and fabrication of power transfer coils and power electronics is provided for a system capable of providing 75 W to a load. At small stand-off distances, 2 inches, and frequencies below 300 kHz, it is shown that there is little difference between inductive power transfer in air and seawater. Measured data shows that at power levels of 75 W, the system efficiency from the transmitter to a receiver and resistive load is above 85%. Keywords: wireless power transfer, WPT, transmitter, TX, receiver, RX, relative permeability, R, relative permittivity, R. 1. Introduction. For unmanned underwater vehicles, UUVs, power is the critical factor that often determines mission lifetime. Unlike many terrestrial vehicles, where batteries can be easily replaced or recharged, UUVs must either surface for battery replacement, or make watertight connections to safely recharge. In both cases, the solution typically requires human interaction, which increases the risk to both the vehicles and operators, as well as raising the total operating cost. One solution for increasing the operational lifetime of UUVs is the use of inductive power transfer to wirelessly recharge the vehicle batteries while the UUV itself remains submerged. Inductive power transfer uses 2 electromagnetically coupled coils to transfer power from the transmitter, TX, to the receiver, RX. For terrestrial applications, this type of power transfer is used for inductive stovetops and is currently being developed as a means to charge portable consumer electronics, cell phones, smart watches, etc., and electric cars. While the commercial protocols for wireless power transfer are useful for many consumer applications, there are a number of challenges that limit their use for UUV charging in the maritime environment. For example, the A4WP standard is based upon a power transmission frequency of 6.78 MHz. However, operating in salt water at this frequency leads to high attenuation and low power transfer efficiency. The CHI standard operates at a much lower frequency, 250 kHz, but is currently limited to power levels on the order of 10 W. The development of a functional underwater wireless power transfer system for charging UUVs is a complex process and requires an examination of many factors, including biofouling, thermal dissipation, power transfer, and communications between the transmitter and receiver. This work focuses specifically on the wireless power transfer portion, and presents the fabrication and characterization of a power transfer system capable of delivering up to 75 W to the load. In this paper, the theory of underwater wireless power transfer is presented first. A high-level overview of the system is provided next, followed by a detailed explanation of the coil and electronics design. The experimental setup used to demonstrate power transfer to a resistive load is then presented, followed by a discussion of the measured power transfer efficiency in both air and water. Finally, conclusions and future work are presented. 2. Design of the wireless power transfer system. A functional block diagram of the wireless power transfer system developed for this work is shown in Fig. 1. The transmit side of the system is comprised of a sinusoidal source, transmitter coil, TX, and tuning capacitor, CTX. For the characterization presented in this work, a function generator and linear amplifier were used to provide power for the transmitter. A more integrated solution of the transmitter circuitry is required for a functional implementation. The receive side of the system is made up. Fig-1, block diagram of the wireless power transfer system. Of the receiver coil, RX, tuning capacitor, CRX, rectification circuitry, and a resistive load. 2.1 WPT coil design. For a set of coupled inductive coils, the efficiency of the wireless power transfer from the TX coil to the RX coil is given as, where K is the coupling coefficient between the coils, and QTX and QRX are the quality factors of the TX and RX coils, respectively. To design a highly efficient system, both the coupling coefficient and quality factors should be maximized. The value of the coupling coefficient is based on the positioning of the coils, spacing and alignment, and the material between them, seawater, while the quality factors are related to the coils themselves, wire resistance, inductance, and capacitance. For the planar coils implemented, it is desirable to align the coils as close together as possible so that the RX coil can capture as many of the flux lines emitted by the TX coil as possible. This means that the efficiency of the power transfer is highly dependent on the quality factors of the two coils. For many terrestrial-based systems, inductive power transfer coils are designed with peak Q values to occur in the megahertz frequency range. While this practice is acceptable for terrestrial applications where air is the transfer medium, megahertz frequencies do not propagate well underwater. Previous work in this area, however, has demonstrated that at short distances, equals 10 centimeters, frequencies under 300 kHz propagate in almost the same manner in water as they do in air. This means that power transfer coils can be designed and characterized to a first order in air with reasonable reliability at low frequencies. The transfer efficiency for symmetrical coil is 3. Proposed system and filter circuit. Transmitter coil is fixed on a stand or a platform and may or may not be submerged on water. Receiver coil is placed on saline water. These two coils are positioned parallel to each other and on an axis passing through their center. High-frequency current passing through transmitter produce magnetic flex which induce EMF on receiver that can be used by the load. Table -1, parameters of coils. Coil wire is made of multi-strand wire instead of single-strand wire, since it has reduced skin effect and proximity effect losses at higher frequencies. The wire is made of 9 strands of 18-gauge wire which has approximate diameter of 12-gauge wire. Wires are wound on a plastic board. 0.1 F capacitor is connected in series to this coil giving resonant frequency at 119.29 kHz according to inductance, L, capacitance, C, and frequency, F, relation. The XR2206 is a monolithic function generator IC that capable of producing high-quality wave of high stability and accuracy. Capacitance between pin 5 and 6 and resistance between 7 and ground determines the frequency of sine wave generated. The frequency F is related to resistance R and capacitance C by the relation. Fig. 4, Wriggle amplifier. The output from XR2206 is amplified by BA1100 and 125W power amplifier produced by Wriggle technology. It has up to 1 MHz full bandwidth and higher than ADV/S slew rate. 3.4 Transmission medium. Transmission is done on both air and saline water. So the parameters of both air and saline water need to be considered. Relative permeability, R, and relative permittivity, R, of air is unity. For saline water relation between R and molarity, M, is given as figure 4. Fig. 5, relative permittivity to molarity plot. Relative permittivity, R, is inversely proportional to molarity, M. Normally seawater have 1 m salt concentration. So the R is taken 60 for calculation. Relative permeability, R, of water is 1. But for salt water it is somewhere between 0.9 and 1. So R is taken 0.9 for calculation. 4 Circuit diagram. Circuit is capable of transferring 25 W power at 119 kHz frequency in both air and saline water. The transferred power is rectified and filtered to give DC out which can be used by UUV or any other underwater equipment. 5 Simulation. Simulation of WPT system is done using MATLAB. All the simulation is done under the condition of saline water by giving 0.9 to relative permeability and 60 to relative permittivity. Fig. 7 is the 3D simulation of voltage, dista NCE and frequency. The maximum power transfer occur at distance 4 cm. Frequency split is present in this distance interval, causing maximum power transfer at two different frequencies other than resonant frequency. Fig 8 shows relation between coupling coefficient and distance. Red line represents saline water and blue line represents air. As distance decreases, coupling coefficient increases but never reaches 1 because of frequency splitting.